So hello everyone, and a warm welcome to our 2025 Quantum Monte Carlo and QMCPACK Summer School. We've been very much looking forward to this, and it's great to see everyone on now, particularly those who are joining from an awkward time zone. So appreciate the extra effort. I'd also like to anyone who will be following the recording, as quite a few people have told us that they'll be doing that, and we try to post the recordings as soon as we can, usually within a day. So I'm Paul Kent from Oak Ridge National Laboratory, giving today's presentation. And while I have the title up, I would like to point everyone at this URL and encourage you to go there and bookmark it, because this URL on GitHub is where we'll be posting copies of the presentation materials, links to the recordings, and also the example files. So in this first session, what I'm going to do is give an introduction to the summer school to hopefully put us all on the same page to begin with. I'm going to go into our aims for the school, a few of the motivations for Quantum Monte Carlo, and importantly, some of the logistics around the virtual machines we've built. So there will actually be a little bit of homework from this first session. And finally, before going further, I shouldn't forget to thank our funders, the US Department of Energy, Office of Sciences, Computational Materials Sciences program. So again, welcome. We've got more than 200 registrants for this summer school from across the globe. Obviously, some joining live, some following the recording. And actually, just to get started, I like to note we, of course, run these summer schools from time to time, but we also do in-person workshops, typically every couple of years, and we had our last about 2 years ago. So actually, it's time for us to have another in-person workshop, likely in the fall of this year or the spring of 2026. And we'll take suggestions for how to most effectively organize that and topics that you'd like to see from the summer school as well as our existing users. So if there's something addition that you would like covered beyond what we're covering in the summer school, this would be a good place where we could cover it. So just an outline of today. I felt it would be helpful to give a little bit of the motivation around, why we're interested in Quantum Monte Carlo and some of the examples of things that can be done with it today. It's based on the questionnaire on registration. We have, a number of people who are very new to the method, in addition to some more experienced folks. After going through that, I'll give some logistics for the summer school, and then talk through how to use the virtual machines that we've built for the summer school. And there's one built with a virtual box for x86, and also one using the UTM software for Apple Silicon. That's very similar. And I thought, why not? We'll actually do a quick example of running Quantum Monte Carlo in this first session, and then we'll take any questions that crop up. So this is very much setting the scene in this first session, so we'll be under an hour, whereas in our next session, it'll be longer, and we'll fully go into the theory behind real space Quantum Monte Carlo. And that's important because it's the foundation for everything that's going to follow in the summer school. So just a note on the Zoom practicalities here. Having questions and interactions really improves these kinds of talks and the school. So please put any questions you have either in the Zoom chat or actually preferred in the workshop Slack that we've got set up. And the Slack, if you're able to use it, is preferred because more people can weigh in, and it's easier to have access to after each presentation. And I'd like to thank Jaron Krogel at Oak Ridge for keeping an eye on both the Slack and Zoom chat during this session. Also, some more acknowledgements. It's quite a bit of effort to put together these presentations and examples for the school. So I'd like to thank all the presenters, Hyunduk Shin and Yilo at Argonne National Lab, Lubos Mitash at NC State, Jaron Krogel and Kahan Saritas at Oak Ridge National Lab, where I'm sitting currently, Ray Clay and Amanda Doomy at Sandia National Labs, and last but definitely not least, Juha Tihanen at Tampere University, who's actually going to be presenting some surrogate methods for geometry optimization within Quantum Monte Carlo, which is something a number of people asked to see. I'll also note that this school has been shaped by previous summer school and workshop attendees based on what they put in the survey afterwards, and we'll also be sending a survey out during this school, and we'd very much appreciate your input. So now some goals for the summer school. Looking at what people had put on in the registration, what we decided to do is really focus on the fundamentals of real space quantum Monte Carlo to provide a foundation for doing practical molecular and solid state calculations with the open source QMCPACK code that we develop. And that is done in combination with other codes, of course, to produce the trial wave functions. And although we support many different codes here, we'll be supporting using wave functions from either the PySCF code on the quantum chemical side or molecular side, and Quantum Espresso on the solid state side. So we're really going to focus on the foundations of good trial wave functions and energetics from Quantum Monte Carlo, because when one has that well under control and has a good understanding there, the rest follows very naturally. One thing we're going to do this time that's different from before when it was requested is in our sixth session, we're going to illustrate some real world research level calculations. So some calculations that have actually been published or will hopefully be published in the coming months this year. So that, of course, this is a little bit of a step up in computational cost compared to what we can run in the virtual machines that we've prepared. But this will then let you see, for example, the statistics that were needed for a particular paper to help shape your own calculations. And then also in a change, we've got some more routes now to provide some follow-on support after the school, and I'll cover those in a moment. Now, if you're interested in more advanced topics, put a note of those in the survey. And as I mentioned, we also have some monthly office hours around QMC and QMCPACK, and there would be a place where we could address them. We also have quite a few prior tutorials that we can point you to. So for example, if you're interested in spin orbit, we're not going to be going into that in depth this time around, but we do have materials on that. So now a note on the schedule. Obviously, you're all here, so you know that we are throughout July going to be running this Tuesdays and Thursdays at 11 a.m. Eastern Time, and we'll go for up to 2 hours. Today will be shorter, it'll be half of that, but typically we'll do like 90 minutes to 2 hours. We won't go longer than that, and we'll have a little break somewhere in the middle. And we'll not just have presentations, but we'll also point to some examples that we've prepared. And the idea then is that you can work through these examples and do your own experiments afterwards. And I'd really encourage everyone to actually do that, because I think the best way to learn these methods, really any method, right, is to start running them, changing some of the variables and getting a good understanding of what happens. And throughout this, we will be keeping a very close eye on the summer school Slack, so we'll be able to answer questions out of hours. And I'll note here that our nominal 8th session on the 24th, that is just a backup, so we'll probably just have 7 sessions, but in case we run into some technical issues or someone can't join for some reason, that's reserved just in case. Fingers crossed we don't need it. So a note here on the schedule, and you can see this on the GitHub site. I won't read it completely, but in the first few sessions, we're going to outline fundamentals of Quantum Monte Carlo. And that's not just going to include the theory, but also, for example, on the computational side, we're going to talk about the computational workflows that we use. And these are, I would actually say, essential, but certainly incredibly useful, because in Quantum Monte Carlo, we are always doing a series of calculations, usually involving different codes. And having a workflow system to handle that for us obviously helps with repeatability and avoiding mistakes. And that obviously helps reproducibility, and it actually adds a lot of productivity. So that's actually the only way I think some of the current calculations that are being published are being done. So for example, some people are now doing calculations on thousands of molecules, and you certainly don't want to try and run those by hand. So after some background, we'll touch on molecular calculations and then solid state calculations with some simple examples. Move on to real world research calculations. So these are a step up in complexity, but you'll recognize the majority of the scripts that are being used as what we've covered earlier in the first introduction. And then a couple of more advanced, well, a bit more advanced topics. First, running on GPUs. I think it's still true that QMCPACK is the only real space QMC code with a full GPU implementation. So you can run on the GPUs that are increasingly out there on the supercomputers down to desktops. And then surrogate methods for geometry optimization with the Stork package. And then I'll wrap up at the end of the 22nd of July. A quick note on the Slack. Hopefully everyone received these emails. It's always difficult to know which ones have made it through the many email filters that there are these days. If you didn't receive an email, if it got filtered somewhere, we have this short link to where you can self-register for the Slack that we're using for the summer school. This is actually one we've used over a number of years, and I've actually always remained signed into that to answer any questions. And so I'd really encourage interactivity here. Ask questions, we can have a discussion. And if you don't use Slack regularly, you may want to go through and mute some of the notifications if you find it's a little bit too chatty for you. Now, how to get support or just questions asked after the summer school? There are many routes, and just pick one you're comfortable with. So we'll keep that Slack channel open, as I just said. We generally would encourage sort of technical questions to be on the QMCPACK GitHub. So in the QMCPACK organization, the main QMCPACK GitHub repository, just open an issue there, and it helps that's public. Anyone can weigh in. And then importantly, after it's solved, people can then find that through search. So that helps other people as well. We also have a QMCPACK Google group. And then, as I touched on earlier, this year we've started running a monthly office hours for general questions on Quantum Monte Carlo and QMCPACK. And the scheduling of that is flexible. We can move it on request to suit you, but typically it's on the last Thursday of each month. We alternate mornings and afternoons to make it a little bit easier if you're in Europe, for example. And there'll be a pinned issue about that on GitHub. And so, for example, our last office hours were just last week. So let me transition now to one of the main two topics today. Why might we be interested in Quantum Monte Carlo? And I thought I would start with what's probably the main motivation for most of us, right, which is tackling the electronic structure problem. So where we need accurate and reliable solutions of the Schrödinger equation for a model of a real material or molecule. Of course, Quantum Monte Carlo can also be applied to model systems, and the code can certainly run for a lot of those. But I think most of us are here for high accuracy predictions for electronic structure of materials and molecular and chemical systems. And of course, we know this is a very challenging problem. Formally, of course, at least in some cases, the Schrödinger equation is claimed to be NP-hard, so that's going to be very expensive to solve to the highest accuracy or to solve exactly. And of course, this was noted by Paul Dirac, one of the fathers of quantum mechanics, about, what, 96 years ago now, where he noted that the necessary laws and equations for a lot of physics, and he claimed the whole of chemistry were known. And the problem, of course, was then solving these equations, and called for the development of approximate practical methods for solving the Schrödinger equation, and I guess also the Dirac equation. Now, of course, we're all going to continue to use a broad variety of methods. Every method is a trade-off and has got some strengths and weaknesses. And so, for example, the workhorse density functional methods that we're all familiar with are, of course, exact in principle, but approximate in practice, which, of course, is fine. But that then leads to some problems if we need a particularly accurate solution, if we're trying to make predictions for a complex many-body phenomena that might not be described by that particular DFT approximation. Or in a case where we're trying to predict a new phenomena, for example, right, and we have no data to act as validation. So clearly we need additional methods, including Quantum Monte Carlo, but we want to have obviously more than one and use them for their different strengths and weaknesses, where whatever approximations there are can be made steadily smaller, right? And also the methods need to be general. So that we would like a method that can be applied to a molecule, but also to a metallic system or an insulator. And then, of course, the interface between those, and if we start doing catalysis, for example. So having a more general approach where the approximations can be controlled is very important. And that, of course, is where Quantum Monte Carlo comes in. And so the idea here in this sort of sketch graph is we've got costs, there's computational cost against accuracy. We want a method that starts out preferably as highly accurate as possible, but then with increasing cost, we can push it towards more exact, towards the exact limit. And of course, we don't necessarily have to push it all the way there, but we just want to assess, roughly how far might we be from the exact result. And this is what people are starting to do with Quantum Monte Carlo. So a few key features, and I'm going to be going into more details and justifying this in the next session, but just a few headline features. The methods are, of course, widely regarded as benchmark methods, and they're very accurate even in their sort of standard or simplest forms. And that's actually the recipe that we are going to be going through in the summer school. The methods are importantly, increasingly affordable, and we can apply them to interesting science problems. And one thing that helps is that at least the nominal scaling, sort of numerically, it's cubic with electron count, but the properties could be plus or minus 1 from that, so square to 4th power, typically. That's quite affordable, and a slightly lower scaling some of the other many-body methods that are out there. And then importantly, as I alluded to on the last slide, we know what the few approximations are. There's not many at all. And increasingly, these can be tested and converged or made smaller. So one can do some sensitivity analysis. And so when we talk to our experimental colleagues, the idea would be that we can give them some idea as to how accurate we think our predictions are, what the absolute uncertainty is. And then finally, my fourth point here, and then I'll move on to some examples, is, and I think this is really a little bit underutilized, is that these are full many-body quantum mechanical methods. So the full wave function is either available there directly, and so potentially a lot of properties could be probed. Also, the choice of input trial wave functions is extremely flexible, and a lot of physics can be put in there. And the advantage for that is that we can we don't need to do simple numerical integrals over basis functions, for example, because of the use of Monte Carlo. So I see we've got a green line here, but hopefully it's not too much of a problem. So let's see if I can clear it. Yeah, good. Thanks for your patience. So I'm showing here 3 recent applications of quantum Monte Carlo. There are, of course, many more. The first 2 here are from quantum materials, and we're done with QMCPACK. The third was actually done with the casino code and is on molecular crystals. And on the next slide, I'm going to show one for molecular systems. So this first one is on the properties of a quantum material, manganese bismuth telluride. And you see here, if we look at the structure, it's got a sort of a stacked structure, layered structure. And it turns out that there can be different stackings of this material, which have very large consequences for whether you have topological states and what the band gap is of this material. And so this is a case where you need van der Waals and charge transfer between these layers to be very accurately reproduced. And that was why Quantum Monte Carlo was used in this study. I'd also note one of the reasons why I picked this was that manganese bismuth telluride is actually a material made from quite heavy elements. And that's an area where we've seen a lot of development over the last few years with quantum Monte Carlo calculations being run over more of the periodic table. Secondly, this is an example of a layered material, chromium triiodide, a study of the magnetic and vibrational properties of this material. One interesting thing that came out of this study was that it has a sort of novel magnetic structure that was a little bit different from what predicted by density functional theory, but something that I can't show here, but that was actually quite important, is that the geometry of this 2D material was actually obtained within the Quantum Monte Carlo method itself. And that actually was in agreement with some independent scanning tunneling microscopy experiments. So moving beyond just total energies, as historically has been done, to now look at geometries as well, done with Quantum Monte Carlo. And in this third example, this was a study looking at the lattice energies of molecular crystals, which is, of course, a very important problem in terms of looking at which organics can crystallize and getting the preferred crystal structure for your particular application. And this is the study of the X23 dataset, which includes molecules such as benzene and urea, acetic acid, and these canonical organics. And the authors claim, that's actually shown here, that diffusion Monte Carlo, actually done with the recipe that we're going to be going through here, finds the quote, same or better reliability as experiment. So that's a big achievement in terms of fundamental accuracy and utility of these methods. So that was 3 examples. Now let me talk a little bit about the elephant in the room, which is of course computational cost. And the point I want to make here is that perhaps the elephant is a little bit smaller now. It certainly used to be a challenge, but many small molecular calculations now only take a few node hours. And as an example of that, I'm showing here the study from Huang co-workers in JCTC in 2023. And they did diffusion Monte Carlo calculations for over 1,000 molecules from the QM9 test set. And you can see some of the molecules that they ran here. So these are relatively small organics, but they're much larger than dimers, right? There's 1 or 2 ring structures in many of the molecules in this set. And in the paper, they gave some notes on the computational cost, and they said that they spent 32 node hours, and these were CPU node hours per molecule. And so that's something that's, I think, these days, affordable for a lot of us. I'd also note, I'm going to date myself here, but And thinking back to when the first defect calculations were done for silicon, this is the paper, so done 26 years ago or so, the silicon self-interstitial defect. If we think about the machines that were around at the time, so this is a plot of progress on the top 500 list, and this green is the top known machines, this performance is higher, and this is year. Well, those calculations will have been done on a machine with maybe 10 teraflop of performance. Well, of course, that's the sort of performance these days that we might find on a single node of a machine, and certainly, a strong certainly a strong workstation could have much more than that. And of course, both of these examples are possible and affordable because they only have up to a couple of hundred electrons. As one does heavier elements or larger systems, of course, the cost goes up, as with any method. And of course, with the statistical methods, it's quite important, as we'll go into, to plan what statistical error bars one would like, so you don't waste compute time crunching them down more than you really need to. Something that I think is quite rare, I think maybe it's no longer unique, but it's definitely rare in Quantum Monte Carlo, is the ability to improve the results and to converge systematically towards the exact results. And this has been demonstrated in periodic boundary conditions in addition to the isolated molecule. And I think this is very clearly demonstrated by Michel Caffarel back in 2016 in some calculations on just the water monomer. And so what they did, this is a plot of the basis set that's being used, with the larger basis set moving towards the left and energy. And what they did was to construct a configuration interaction expansion using selected configuration interaction methods. So they grew the number of determinants they had in their calculation. And noted here as a reference, they plot the full CI result. And then they have this selected CI known as a CPC result, where they've post-processed that with diffusion Monte Carlo. And that's the more accurate quantum Monte Carlo method I'll be describing in the next session. And we see it improves on the full CI result, which is of course interesting. And then they extrapolated to what, at least at the time, was the most accurate water molecule calculation that had been done to date. So that's one way of improving the accuracy in quantum Monte Carlo calculations. There's a few others. Of course, there are other technical convergence parameters that need converging. Most notably, of course, in a periodic system, the cell size has to be large enough. But the way I like to think of this, at least informally, is now we have a pay more, get more method, so as we can increase the computational cost and steadily improve the accuracy of the results if we want to. And that was something that wasn't done until maybe 5-10 years ago. And one other example I touched on, of course, the many-body physics is there. We have access to the wave function in many of the methods, so we can compute essentially any property. So for example, the interacting density matrices could be obtained, as could momentum distributions and many other examples. So we could look at beyond single particle physics. And I think this is a little bit of an underexploited area. And I'll just show you here, this is an example from a paper by Ilkka Kalampa. This will take too long to explain all the details behind it, but they're looking at the change in momentum distribution in vanadium, so challenging correlated material, through a structural phase transition. This is also an example looking at the structure factor by Yang and co-workers, looking at an electron gas which has got gates around it, and learning about the properties of that electron gas. And one thing they also did in that actually was to make a density functional for this system from the QMC results. All right, and my final example here before I switch topics is an area that I know many people are excited about, which is the use of quantum Monte Carlo data in machine learning. And here on the left, I've got an example of using machine-learned interatomic potentials from QMC data. And on the right, I've got an example of an area where QMC hasn't been used yet, but probably would be in future, possibly by someone on this at this summer school. So machine learned interatomic potential. So what the idea here is, instead of using training data from density functional theory or quantum chemistry to go ahead and use Quantum Monte Carlo data. And in this paper from the Banner group in 2023 in PRL, they studied the hydrogen phase diagram with a machine learned interatomic potential, so a classical potential that had been taught by data from Quantum Monte Carlo energies and forces. And this is an example where you'd really like to have a highly accurate method and one where you can improve the approximations that are being made, because, of course, there isn't as much experimental data here as one would like, and that experimental data is also subject to interpretation. So having a really accurate many-body method is advantageous here. And just moving on to the second example, or potential example, one question I would ask is, whether we're going to be seeing more DFT approximations created from Quantum Monte Carlo. And of course, that would close the circle with the original homogeneous electron gas calculations done in the 1980s. So this is an example of large-scale density functional calculations that were done by Vikram Gavini at University of Michigan, this group a couple of years ago. So they did very large-scale DFT calculations to look at the effects of different structures in alloys. So they really needed the length scale. But one thing they did there is they machine learned a DFT from, in this case, it was quantum chemical data, but they actually called for many body data, and other people have done that as well. I'll also note for those following this, there was recently the scalar functional from Microsoft, and earlier the DeepMind 21 functional using some quantum chemistry data, and of course Quantum Monte Carlo data might well play a role in future versions of these kind of efforts. So this is an area I'm very excited about, and I know several people online are as well, because it seems that machine learning will provide several routes actually to upscale these high accuracy results to the larger length and time scales that would otherwise not be affordable. All right, so let me now switch topics after what I hope is that interesting motivation and a little bit of background and what can be done with the methods. Let me talk now about using the summer school virtual machine. So what is the summer school virtual machine, first of all? Well, what we've done is made a customized Ubuntu desktop with installed versions of QMCPACK, the Nexus workflow software that comes with QMCPACK, Quantum Espresso, and PySCF installed, as well as the various summer school files. So you can use this and start running calculations straight away without having to install any additional software. On x86, we've got an example using the VirtualBox software, and on Apple Silicon, so more recent macOS, we use UTM. We try to size all the examples to be a modest-sized laptop, so we've assumed 4 cores and 8 GB of memory. But if you're able to, obviously use this on the most powerful machine that you have ready access to. And although we're only going to really get started running examples in depth by the 3rd session, please try earlier so that any problems that arise can be debugged. As obviously there's a lot of moving parts that need to come together when one sets up these virtual machines. So how to find the installation instructions? Well, if you go to your bookmark for the QMC Summer School on the GitHub site and look in the README, you'll see here there's a link with going down to instructions on how to download and use the machine image. And I'm going to go through that now and actually show an example of a little recorded movie of setting up both the VirtualBox and UTM examples. So how to do this, and I'm essentially talking through the instructions that are in the README, so this isn't any different. We know from experience that some people will be very used to this, but for some others, this will be completely new. So we're going to talk through the steps. So first of all, you need to get hold of VirtualBox, which is a free download from the VirtualBox site. You might also be able to get it via a package manager. And the key step then is to then download our virtual machine image file, and we have this short link. Now, this file is about 5.5 GB, so just under 6, and it's hosted on box.com. But be patient and try downloading again if you have any issues downloading it, as it may take some time to come down, even if you're on a fast network. And then what you do is you run VirtualBox and then import that image to set up the virtual machine. I'll show that in a moment. So you go File, Import Appliance, and then import this OVA file. And then one important point is that when you're importing the so-called appliance, I'd encourage you to change the CPU count and the memory to match your machine, because you'll be able to do more if you have an appropriate core count and are not trapped on the 4 that we've got by default. And certainly increase the memory if you have more. This should be 8. So what does that look like? Well, I've made a little movie here, which hopefully will play. Oh, yes, there we go. So we go to import, and this is in VirtualBox. We find wherever we put that file. In this case, I've got it here. Go to open, hit next, and then we double check the CPU and RAM is sensible for our system, and hit finish. And it will then import the appliance. And I did this on quite an old x86 Mac, so this actually takes a minute or so to go through, so I have to be a little bit patient here. Let's see if I can go further. No. So I'll just wait for this to go through. Yes, certainly do this on the most recent laptop and workstation that you have access to. I will go through some alternatives in a few slides after showing the UTM version of this, which is a little bit faster, fortunately. All right, so we're painfully watching that progress bar move non-linearly. All right, so to start it, hit the green arrow, and then the machine will power up, and we'll get to a desktop. I won't wait for this to go all the way through, as we'll see this for UTM as well, but eventually we get to an Ubuntu desktop here. One important point here, and this is also in the README, so the user is called QMC user, and if you need to authenticate to, for example, install some software, as you can do that, the magic word you need to authenticate is QMC 2025, and there are no quotes around it. And obviously you should change that if you're using this virtual machine for anything beyond the summer school. So executables like QMCPACK and QMCPACK Complex and pw.x from Quantum Espresso are on the path. They're also in $home/apps. And of course, since this is a full Ubuntu desktop, you can use the package manager, which in Ubuntu is apt-get install your favorite piece of software. So perhaps you want a particular editor, you can get to it that way. What about the Apple Silicon route? Well, we use the UTM application, which is free. You can download it here. But I'll note that if you find it useful and want to support development, you can also buy it via the App Store. You download the image file and note that it is a different link to VirtualBox. Similar size, and again, please be patient when downloading. Perhaps try at a different time if you run into issues. And then it's very similar. You need to import the virtual machine, and in UTM, and I'll show this in a minute, you create a new virtual machine and then open an existing one. And again, edit the settings to suit your computer. Let's show this. So we go create a new virtual machine, open an existing one. There it is. And we hit the play. Oh, if you can go to edit, you see the CPU cores and the memory, so you can change that to suit, and you hit the play button to start the virtual machine, and I'll let this one run. I used a much more modern laptop for this. So Ubuntu will boot, and we will end up at a desktop in a moment. All right, there we go. And hopefully that's familiar to a lot of you. There it goes, just resized, and QMCPACK is on the path, as is everything else. So I hope that's a smooth process for everyone. Full instructions are in the README, but hopefully going through those movies were helpful if you've not seen any of this before. So what are some alternatives to this? So for example, if you have a particularly weak laptop, one possibility might be to run VirtualBox on a remote workstation and use LX11 or some remote desktop type software to access it. Another option, and these are would be, if you actually have an Ubuntu machine yourself, you could run the setup script directly, but please carefully read that script and understand what it's doing because it's going to run the package manager and it's only installing standard software, but you should make sure you understand that before running the script. On a Windows machine, hopefully you can run VirtualBox, but if you're a user of Windows subsystem for Linux and you have an Ubuntu 24 or recently, you could just run the setup script directly. That would work well. That's something we've tested. And a final option here, and this is actually really the best route if you've got the interest to do this, would be to just install the software directly on whatever machine you might use for research. So you can look at the setup script and just adopt that for whatever relevant Unix you have by perhaps changing the names of the packages or asking your system administrator to actually do a similar installation. And of course, the advantage of that would be then that you have the software set up for your own research. And as best we can, we'll provide support through that through the Slack. And I'll note every time we've done a workshop or summer school of some kind, a few people have done this historically on their own initiative, and they've been successful, and that's been quite helpful. So that's also a route that we know works. So the installation script and instructions are again in the summer school GitHub repository in the virtual machine folder. And I'd also note we have quite extensive instructions for QMCPACK in the online manual on Read the Docs. And so there's examples for a lot of different operating systems, different Linux distributions. And also we have some setup scripts for many different supercomputers. So that can be used as inspiration. And my recommendation here would be just ask on the Slack and ask us what we think the best route would be given your situation. So those are some alternatives. I'd encourage everyone to get one of these virtual machines installed. Of course, it's completely okay just to follow along the lectures and presentations, but I think getting some hands-on is really the best way to learn a new method or to get familiarity with a different code. A little bit of housekeeping now. So we will be updating that summer school Git repository throughout to put presentation materials and new examples on. Probably just before each session on the Tuesdays and Thursdays. So you can go in and do a Git pull to update. And we're going to try and avoid the need to do any re-downloads or rebuilds. Fingers crossed that's not going to be necessary. And so now I thought, just here in some of my penultimate slides, I thought, well, why didn't I show a quick calculation? And so actually there is an example running the water monomer. If you have the virtual machine set up, you can go to the summer school directory, session 1 introduction H2O example, and there is a README there giving some steps to follow. And this is actually an example we have in chapter 1 of the QMCPACK manual. And there is an input file that uses a pre-made trial wave function to compute the energy of this single water molecule. And it does variational Monte Carlo and then diffusion Monte Carlo. And on my more recent laptop here, it takes about a minute. So this is a very quick calculation. And of course, as I'll be describing on Thursday, diffusion Monte Carlo is the more accurate calculation, should give lower energies, and that is something that we'll be seeing here. So you can do an MPI run uh, of QMCPACK, so MPI run minus N4 QMCPACK in the name of the input file. This will be one of the few times that we run QMCPACK directly, actually, in this summer school, as opposed to running the workflow system, which is Python. And I have here some examples of how to do the analysis. And I've made this a little bit more verbose than necessary. So we have an analysis tool called QMCA. And QMCA knows how to analyze the output files from the calculation. And these are text files. You can have a look at them, and they end scalar.dat. And so what I've done here is said, yes, analyze the energy invariance, disregard the first 20 blocks of equilibration, which is very generous. And I would like units to be in electron volts. Otherwise, we'll get atomic units energies. And then and that's something you can also do is ask to plot a trace of the energies and get a graphical plot. There are some reference output files in the results you can have a look at if you don't want to run the code directly. And an exercise to try here, and if you look at the end of this input file, it should be very obvious what's going on, right? The statistics are done as a series of steps in the Monte Carlo, and the run is divided up into blocks containing a number of steps. So if we increase the number of blocks, we should get a smaller error bar. So that's actually something that one can do very straightforwardly here. So for example, if we have 4 times the number of blocks, we will have 4 times the amount of statistics, and that should halve the error bar because, as I'll be touching on in the next session, since we're doing Monte Carlo, the error bars will scale as 1 over the square root of the number of samples. And that might seem like a very simple check, and it is, but it's actually one that I really like to do when studying a new system, because, for example, if the run isn't equilibrated, then we won't get that trend, and we'll be able to see something is not quite right or something is misbehaving. So that's always a good check to do. So just to show what that looks like when you plot the trace, these are the energies from many blocks. This first part is the variational Monte Carlo, and then this is the diffusion Monte Carlo, and it's less noisy because there's more data per block, the way I've got it set up here. So we'll be explaining this in subsequent sessions. But if we look at the energies here, the VMC run ends in 0.39, and the DMC energy ends in 0.65. So lower energy, a bit more accurate. And that's this red average line is a little bit lower on this plot. So a quick taster of running perhaps your first Quantum Monte Carlo calculation for a molecular system. So now, penultimate slide, and then I'll see if there's any questions. So there's a few things to do here. So if you haven't yet, register on the Slack channel. As I've explained, we'll be doing support there, and we can have much discussions much more easily than we can on Zoom. And then go ahead and install that virtual machine using the instructions on the QMC Summer School repository, and then try running the water molecule example. So that's that. I hope that served as a useful introduction and sort of foundation for setting what we are aiming to do in the summer school. I'll open up for questions in a minute, but note that in our next session, we're going to be really switching tacks and focusing on the fundamental theories behind real space quantum Monte Carlo, so the foundation for what follows, and I look forward to seeing everyone there.